Hi guys, so today we're going to learn about DNA, its structure, how it replicates, and then the importance, the function of all this. So right here we have a basic strand, and of course it's not our double helix that we're used to seeing. So there's my double helix. So it's not that we're used to seeing. We're flattening out so we can see everything that's going on. So what's going on here is we got a phosphate group, we have a deoxyribose, and then it's stair steps on each side. All right? And these are our backbones of our DNA strand. One end always ends in 5 prime. So if this end ends in 5 prime, then this one will end in 3 prime. So we have a 3 prime up here, so that means this has to be a 5 prime. So inside all of this, we have a C, a G, a T, and an A. So our G is guanine, our C is cytosine, our A is adenine, and our T is thymine. And these are our nucleotide bases. All these together are held in that helix that we know and love by a phosphodiester bond. So now that we know the ends and we do know the basic structure of DNA, we're going to jump right into DNA replication. So we're going to start out with our DNA strand. Very, very crude, but this is our DNA strand. What happens next is a helicase comes in and says, here's some DNA that needs to be separated and copied and initially just replicated. So our helicase comes in, binds to this origin, and splits it. Creates a little bubble in here. So here's our bubble where the helicase went in. So now we're just going to work with part of that bubble. So we're going to make sort of like a Y and separate it. So here's our DNA, ready to be translated, waiting on its turn. And we're going to call this side 5 prime, 3 prime. So down here, since this is a 3 prime, this has to be a 5 prime. And this will be a 3 prime. It does it all the way around. So now we're ready to start the replication business. But we have to add something. We have to add a RNA primase. An RNA primase just tells everything, hey, it is time to start adding these nucleotides. So what comes in after the helicase is there, after the RNA primase is there, is a DNA polymerase. The DNA polymerase just attaches and flies on down. So, since this is our 5 prime, this would be our 3 prime, 5 prime. DNA adds nucleotides from a 3 prime to 5 prime thing. So, or 3 prime to 5 prime fashion. So there's our nucleotides. This DNA polymerase has done its job. It's flown through. And this is our leading strand. It's the strand that it can fly on through. It can generate all those nucleotides in a timely fashion. So now we're going to get rid of this, just to avoid confusion. And here is the RNA primase. we gotta think, this is 5 prime, because this is 5 prime, so this has to be 5 prime. It can't do anything. We can add nucleotides 5 prime to 3 prime. So what happens is the RNA primase comes in and attaches at multiple points throughout the segment. So right here, we have 3 places where our primase is going to join. So our DNA polymerase comes in and does the same thing. So now we are adding nucleotides in this direction because it's going from 3 prime to 5 prime. But it has to stop each time because it has to, the DNA polymerase has to attach to the RNA primase each time to add these nucleotides. But we still have them. All right? This is called your lagging strand. We can see why, because it's still going just as fast as this, because DNA replication happens very quick. But this does lag behind just a little. And each of these fragments, we have 3, 1, 2, 3. Each of these fragments are called Okazaki fragments. So, let's say everything has done its job. We have our new DNA strands, but this one has a RNA primase, and this one, since it's our lagging strand, has 3 RNA primases. So what has to happen now is an exonuclease comes in and removes all these. And therefore, the place where the primase was gets replaced with its corresponding nucleotide. So here's the nucleotide, and they each just replace what was there. So if it's A, adenine, then we got a thymine. If it's C, cytosine, then we have a guanine or a G. You would think we would be done, but not just yet. Now we have to have DNA ligase come in and go through both of these and make those phosphodiester bonds to keep everything together. So it creates those bonds, and then the DNA starts twisting and creates a double helix pattern. So we have 2 now new strands of DNA, and that is DNA replication. So what's the importance of all this? Why does this matter? This matters because if there's a mistake made here and the mistake is allowed to go on, then this could create a mutation, which we'll learn about countless mutations later on in the week. And let's say our cells in our body. We have all our cells in our body, except our neurons, are replaced on a regular basis. Our cheek cells are replaced. I mean, how much saliva can we go through in a day? Our stomachs replace cells constantly because they're projected to this acidic environment. So they have to constantly replicate and constantly remake themselves. Our gametes, our sex cells, the sperm and egg, we have to create those in order to have new babies. And so the DNA in those cells, all those cells, sends messages out saying, hey, it's time for us to replicate. It's time for us to make copies of ourselves. Or the DNA inside the nucleus sends out a signal that says, this needs to happen to us, the cell. Maybe we're hypophobic. We need to get rid of some water so our solute is balanced with the outside world. And that's it. I'll see you guys tomorrow. Bring some spit. We're going to extract your all's DNA and have fun.